Hi there folks, hope you're well. We're going to be having a look at the flexural formula, how it's derived. I don't expect you to derive it or whatever, but I expect you to be able to use an equation. So we'll do this and we'll do a couple of examples. Okay, the flexural equation is all about the bending of the beams, of a beam, or beams in general. And it's how you work out the slope and deflection and other associated conditions that happen when you bend a beam. Right, we've got a beam here and fixed at both ends, or supported at both ends. Simply supported beam, this is called. From A to B, it's got a load of W acting at the centre, and we have your neutral axis across here. And what we're going to do is kind of imagine there's a load on there and how it would deform the beam. It kind of look something like that. Not as pronounced, obviously. You'll find that if you have a beam of a few metres, the deflection will only be a couple of millimetres in general, and it will always stay within the elastic zone of the material. If it ever goes out the elastic zone, it will deform and the beam will fail. Right, so before bending, this kind of represents the beam, and this is a section we're going to look at here. And again, this is the neutral axis. One thing you have to remember about when we're looking at beam bending is you have, for instance, if it's bending, if it's sagging in this direction, above the neutral axis you will always have compression. This is for a simply supported beam like this. It can change depending on the setup, okay, but on the bottom here we're always in tension, i.e. this is getting compressed together. If you look at that, you can't imagine, and we'll draw on the neutral axis on this one. And one thing, it kind of looks like it does there, but we always have to assume the neutral axis doesn't change length, or we know it doesn't actually change length. Above it you have compression, below it you have tension. At neutral axis it doesn't have tension or compression. Now you say to yourself, well, with that, at what point does it fail, this thing? But what you'll find is, say for instance, say you had a flat wooden plank, see, like a scaffold plank, and you were walking over it with your wheelbarrow, say on a building site or something like that. Now that'll sag dramatically, and what you'll find is, what tends to happen is the bottom here, the tension will rip the fibres apart, and that will fail when that occurs. Now that will fail, that separation of fibres and failure will occur before any effect on the neutral axis. In other words, the material here will fail before you can see the neutral axis changes. Anyway, that's a wee footnote. Right, and we're going to look at a little bit of this section here, and we're going to look at, imagine if this is a beam like that, we're going to look at this plane here and this plane here. We're going to call that then E, F, G and H. And this GH is a distance from the neutral axis. We're going to call this distance y. And we're saying that y, this is the y-axis, and along here, x-axis. And we're going to call this little piece that we're looking at, this little sliver or slice, we're going to call that dx. Now, yeah, this is before bending. I'll go over here, I'll do a little drawing of the beam after bending. Right, so this is a beam bent. We're going to call this A, in fact, this should be C dash. Right, so we're going to call that A dash, C dash, B dash, B dash, D dash, and this neutral plane here, E dash, F dash, and G dash, H dash. But what I must say, we are just looking at the elevation of this beam. We're just looking at the length, the lengths here. We're not taking into account any of this area in the background here. So we're just looking at the lengths here. Now, I'm just wanting to talk a little bit about the radius of curvature here. What we're talking about here is from the neutral axis, if you were to, because what's happening here, this is a rectangle here, or square. When this bends, these are going to be under compression and they're going to move towards each other, and B and D is going to move further apart. So if you trace these back, you'll find there's a point where they intersect. Here's the centre of curvature, and the distance, this distance up here, is called the radius of curvature. Now, if you imagine you've got a line here, and that line is a length L, say, whatever, or just, well, so now if you start to rotate this round, what you'll find is when that's just a straight line like that, the angle here is 0, and that means that in that situation the distance here is going to be 0, like as in the length of this arc here, because this hasn't moved anywhere. And the more this goes round here, the longer this distance gets, and it's directly proportional to the increase in the angle here. And when you get to a point where, say something like that, where, I'll get rid of that. If this is obviously the radius, and again this is the radius, and the length of this arc is a radius, that's when you get the angle here is 57.3 degrees. And if you multiply that by 2 pi, that equals 360 degrees. Can you see that? So that's why in engineering you use radians. So when you look at, I don't know if you do single phase electricity or anything that, or in dynamics, anything that goes round 2 pi radians means it's went round a full circle. And, or as I say in alternating electricity, you would get the frequency 2 pi f is related to the cycle. That's like 1. Say in other words, if it was a frequency of 1, 2 pi times 1 would be 1 hertz, basically. Or 2 pi 10, a frequency of 10, that's going to be 10 hertz, because that's 10 circles, 10 full cycles. Anyway, just another footnote. So basically what I'm saying here, if you're working in radians, and I want to find the length of this arc here, it's going to be this one here in particular, so the neutral axis would be r times the angle in radians. So that would show that EF or E dash F dash would equal that. Right. So if we were to imagine that this has a length to go to here, well, it's this Y here, and then so this distance here is going to be R plus Y times angle in radians, obviously. I'm just going to reiterate this again. Say that's a radius and you went round half a radian. That there would be half the radius, if that was half a radian. Just to reinforce that into your heads there. Right, so where were we? So this length G dash H dash, this length here, remember that's been stretched by this Y amount, is going to equal R theta plus Y theta. Right, I'm hoping, hope this is making sense, right? But if we look at this part, we know that GH was equal to EF before it was bent. Oops, EF. Now, what we're looking for, when we look at the tension here, or the strain, which is the change in length, we are looking at this and saying, well, what is the change in length between this one and this one, this GH and this GH? Well, it's going to be the stretched one minus the not stretched one, and that will leave whatever was stretched there. So it's going to be, and remember, if this length is the same as that length, well, that means this GH is going to equal R theta. I'll push this up a little bit so you can see that. So therefore, the delta L of GH is going to be R theta plus Y theta minus R theta, which equals Y theta. So the change in length is equal to Y theta. And we know that the strain is equal to the change in length over the length, and the length initially was R theta, so we're going to get Y theta over R theta. Obviously they'll cancel, so that equals Y over R. So far we have the change in length equals Y theta and the strain is equal to Y over R. Now remember, Young's modulus is equal to stress over strain. We can rearrange that to strain equals stress over Young's modulus. And we can see that this is the stress from the bending, from the load causing the bend. This will be the stress, the force over the area. And so therefore we've got the two equations there that we can add together, which is going to be the bending stress over Young's modulus equals y over r. And we'll call this, let's see, rearrange it to its more kind of commonly form as the bending stress divided by y equals Young's modulus over the radius of curvature. So that's equation 1. Now, what I'm going to do is, if you think about what we're doing here, we've got a beam and we are just looking a very small part of that beam in reality. Now, this is, I've called this dx. Now, you've come across this in calculus many times, I'm sure. And one thing about this is we always say we limit this to, we say the limit will tend to 0. What that means is this distance here, you try and make that as small as possible, so it's kind of like I don't know how to really describe it, like it doesn't interfere with what's going on. I don't know if you know what the word calculus in Latin means pebbles, and I always imagine that as having a big beach with loads of millions of pebbles, and if you take one little pebble off that beach, you're not making any difference to the volume on the beach, really, in real terms, because there's millions and millions of these. Nobody will notice if you take one, but on this one is encoded the characteristics of the beach. It's like taking a sample, and this is like taking this little sample of that little sliver of that. And what we're going to do is we're going to look at, so for instance, if we've got a tiny bit here, and if we think about it, say this was like a slice we were taking about, so that ends up, if you're looking at it, that becomes an area. I don't know if you can see that. And in terms of x, the x, in this situation, you'd probably, if y is going that way, that would be like your z plane, I suppose, kind of like x, y and z being the depth of your beam. You get you end up with an area, but that area is still in terms of this tiny little bit here. So if you're wanting to kind of find the area here, you would have to, instead of just looking at, say you had a beam like that and you wanted to find the force on all of the area rather than just this dx or dA, you would have to integrate, like as you do in calculus. You have to integrate these values, and that's when you look at, say for instance, you've got your velocity time graph, and see that's no, and yeah, that carry on. That's v. So your dv by dt. That's you just taking a tiny sliver of that. That's kind of the equivalent of what we're doing here. But then we have to integrate it to get it what it would be like for the as a whole, not just a wee piece of it. So if we're looking at the bending stress, which is, and we had that over y equals modulus over the radius of curvature. If we, because what we're thinking about here, we want to find out the bending stress is going to be df over dA, right? And that's going to be the force that's applied over the area of the beam at the top, right? So the stress, the bending stress, is going to be equivalent to this, right? So we'll just leave that there just now. And what we're wanting to say, well, what would be the force required for that? So dF is going to equal bending stress at B times the area there. And this is because obviously the stress equals force over area. Well, that's making sense. You should be able to remember a lot of this from last year. Now, if we want to take a moment acting on the area there, let's see, the moment is going to equal the force times y, being the distance from the neutral axis. Remember, on a beam you have your neutral axis, and the plane we're looking at, this y distance, will affect, if you've got a moment round there, the distance from there will be multiplied by the force, just like you would do when you take moments normally. Also, this wouldn't be a capital M here because this is smaller. This has a dF there and a dm then. In other words, this is only the moment over this tiny area. So a small moment over a small area. And to find the moment, what we would do, we'll substitute this equation up here into here. Right? And that is going to give us this equation up here into here. Right? And that is going to give us, so we can rearrange the bending stress to be E y over r. So looking at that and that, dm equals E y r dA times y, which is going to equal dm ey equals ey squared dA over r. So now we need to integrate both sides of this. So let's see, integrate dm to give m is going to equal the integral of all this e over r y squared dA. Now these are constants. It's like if you got 3x squared, you can just integrate the x squared and multiply by 3. So you can take these out. Oops, e over r y squared over dA. I don't know if any of you remember, or if you can remember this here. The integral of the area on the y-axis squared. Remember what that is? That's the second moment of area. So you can replace this here with I. So that's going to become m equals e over r times I. Or m over I equals e over r. If you can see that there. I think you can. Right. So then we can just, we'll call this equation 2, I suppose. Then what we can do is just combine these. Combine these equations to give us the main flexural equation, which is m over I equals e over r, which equals bending stress divided by y. There we go. And it's handy for checking out the different variables and conditions that occur when a beam's bending. And we're going to do a couple of examples on that. What I'll do is I'll send you out a tutorial and I'll go over the examples in the next week or so. Let's see. Right, so, and this is your maximum bending moment, second area for the whole beam. This is your bending stress, R is your radius of curvature. I don't know if you can read that. This is Young's modulus. And this y, this is the distance. If you're looking, oops, that's not drawn very well. So you've got your neutral axis, and you're looking at, say you're looking at this layer here. The neutral axis, the topmost layer is the distance y you're looking at there. And generally you would say it's positive y in this direction and negative y in this direction below the axis. What I'm going to do now, while I've got yous, is I'm going to have a quick look at stress, moment and strain profiles, or profile for a beam, which kind of help you visualise the forces involved. Right, imagine we've got a beam here. This is the neutral axis, and say this is your distance y from neutral axis to, see, that's the top of your beam, and down here is like minus y. Right, now you can imagine that, see, like that was the, see, like that's the magnitude of the force of for this one. See compression. See if it's getting no, this will be in sorry, in tension. Sorry. So this is in tension. The beam's bending that way, and the top part of it is going to be in compression and tension. And I hope you can kind of see that. See if you're on the neutral axis, there's zero compression or tension, and the further up or the bigger y gets, the bigger the force of the compression becomes. Yeah. Could be written, I suppose, in terms of, you could say, your strain, going like that. And obviously the bigger y is getting, the bigger your strain is getting. With your, let's just say, your elongation and your compression there. And this slope here is actually y over r, this slope here. So let's see. And up at this top point here, you would have your E max, and again E max here. Now if we were to let's see, draw our wee line here, and what we want to do, if we were to multiply this by Young's modulus, what it will give us is the stress. Wait a second. And again, the stress is increasing the bigger y gets, or the distance from the neutral axis. Again, you'll have your maximum stress at this point. Now, what you have to remember as well, this is a 3D beam, so it has like a width, and if you can kind of imagine it kind of like that, it's kind of like saying it's like a wedge of force, because this is a volume. Looking at it like that, and you could see that as a force wedge or something like that, I suppose. And again, looking at this here, this is your neutral plane, with the area there, and below that you get your maximum stress and tension, maximum stress and compression. And again, this would look like what the best at drawing, something like that. Oops, I don't know if that looks, that's not too bad, I suppose. And that's how, so it's quite handy to be able, you can kind of visualise what's going on with this. And you would say this is like the x axis, this is y, and this is z, or z as they say in America. Now, if you imagine you have a moment in that direction along the z axis, you know, compressing it like that, and a moment coming this way, obviously that'll be a positive, a negative moment, positive clockwise, negative anti-clockwise, a kind of twisting along, so you'd have a compressive sort of twisting, or a tensile stretching sort of thing going on. It's quite handy to help you visualise your strain and stress values. Okay, hope you enjoyed that as much as I did. I'm going to send out a tutorial with this, and I'll let you have a go at that, and I'll send you a video of me going through the answers in the next few days. The next video, oops, should be picking my nose. The next video is I'm going to look at slope and deflection. You get equations that have already been figured out for different beam scenarios, and depending on what sort of beam you're looking at and how it's supported, you can just apply these ready-made equations to them. Although you're never really going to get a beam in real life that's going to be as easy to manipulate as that. They'll have different loadings, different weightings, different supports, whatever. So you have to kind of tailor your equation to suit whatever design of beam you've got, or what have you, whatever loads going on top of it, or whatever. So you have to use this thing called Mccauley's method, and what that allows you to do is, for whatever beam you've got, it allows you to make it to like individualize an equation for that particular beam, and it allows you to get the slope and deflection at any point of it, which is handy. Obviously, you remember what slope and deflection are, don't you? Are you sure? Do you want me just to quickly go over it? Your slope, excuse me, your slope here is, if you've got a load there, it bends that. Your slope is, so basically this is going to be like bending down the way at a particular angle, depending on the load, and it's this angle here is your slope. Now there's one thing that happens when you get to this part, slope is going to be 0 at this point, and it's going to be maximum at these points. This is handy when it comes to Mccauley's method, because it is what they call boundary conditions. So the slope has a boundary at this point where it equals 0. The deflection is the amount of distance that's travelled in, say for instance this direction. Say that was x, the y, that's the y direction, and it is how far it's moved basically. So it moved less there, you get bigger, so you get maximum deflection. Say for this type of setup with two supports and one weight, you get maximum deflection at this point. But at these points on the beam, there will be like 0 deflection. You can see, because obviously they don't move, do they? But this moves, and it moves a distance y, and maximum there 0, 0. And this is handy because you can use that when you're working out using Mccauley's method to work out the equation of bending and slope and deflection for the beam you're looking at. Okay, thanks for listening. I hope all that made sense. As I say, I'll send you the tutorial, and I'm going to do the next video on Mccauley's method very shortly. And what I was just talking about there, the boundary conditions there, are very handy when you're using Mccauley's method to create the equation for your beam. Okay, cheers.